Okay, so I'm hoping that from the intro video you remember that the derivative, and I'm going to be real generic here, I'm going to say the derivative of natural log of something, whatever, is going to be 1 over something times the derivative of whatever that something was. Is that good enough? That's very generic. That's okay? All right. So when I look at number 5, it is the derivative of natural log of something. And so that is going to equal 1 over that something. You can't see it. I need to fix that. Thank you, Dax. How about that? 1 over whatever. In this case, it's 1 over 3x squared plus 9. But then according to the chain rule, as we've been doing since almost the beginning, you have to multiply by the derivative of the inside. So in this case, we multiply by 6x. So a number of ways you could clean this up. Obviously, you could rewrite it like this. And then if you wanted to reduce the fraction down to lowest terms, doesn't the top and the bottom have a common factor of 3? So if you wanted to, you could certainly write 2x over x squared plus 3. That would be just as good. Okay? To be honest with you, I would take any of these 3. To me, they're all correct. They're all numerically the same. Okay, so yeah, what do you think about number 5? Any questions that come up there? Okay, fair enough. So then number 6 says derivative of the square root of natural log of x, and I'm hoping that, as we have customarily done, maybe you rewrote this as the derivative of natural log of x to the 1/2. So I think when you do it that way, it becomes a little more clear that you've got a chain rule here. But instead of the chain rule involving like a function being put into ln of x is actually the inside of the chain rule, right? So the outside function would be the 1/2 power. So I'm hoping that you did something like this. 1/2 natural log of x to the negative 1/2. But then we still, again, chain rule, we have to multiply by the derivative of the inside. So on this one, what would we multiply by?
1
Times 1 over x. That's right, because the derivative of natural log of x would just be 1 over x. So that would be a perfectly good form. You could do a lot of simplifying with this. For instance, you could have something like 1 over 2x root ln of x. I think I did all that right. That would be a way you could simplify this down, and that would be just as good. But seeing as that's just as good, I can't see a real good reason for you to keep going, right? Unless you just were determined to. Whatever. Okay, so there's 2 of them, number 5, number 6. We doing okay? I think you guys are going to find this chapter to be, maybe for some of you, maybe a little more to your liking. There's going to be less like reasoning from theorems and definitions, and a lot more kind of, here's a principle, here's why it works, now let's try to apply it. If that makes sense. Hopefully you're seeing that right here. Okay, and then number 7, the last one up there on the screen. Remember that this is ln of x squared. So it's obviously it's a multiple composite, a double composite. And so if I'm going to differentiate this, the first thing I need to do is identify the outside function, that's ln, and then the inside function would be, for now at least, natural log of x squared. So the derivative of natural log of whatever is equal to 1 over whatever it is. So it's going to be 1 over natural log of x squared. But then we have chain rules, right? So now I have to differentiate just the purple function. So the derivative of natural log of x squared would be what? 1 over x squared. And then my tiniest of boxes, the most inside function is just x squared. So I get to multiply by 2x for my final chain rule factor. Okay, so we could, of course, clean that up quite a bit. But for the moment, that's a good answer. Do you have any questions on this? So if I cleaned it up a little bit, obviously one of the x's would cancel out. So we'd end up with 2 over x times natural log of x squared. I suppose you could say that's the most simplified version. Make sense? Okay, all right. Is natural log friendly? We good? Okay. Give you just a minute to think there's anything you wanted to say about any of those. Bless you. Who would have thought? In the video, I talked a little bit about where natural log actually comes from, right? Integral from 1 to x of 1 over t, right? You use an ln for a while. Who would have thought? It's actually a calculus thing, where it comes from. Okay, so you guys have had plenty of opportunity to say something. You okay? Okay, cool. So then let's take a look at number 8. Number 8 is kind of a cool combination. I would say this is definitely a calculator active question. And so if you don't have your calculators out, go ahead and do so. This brings back an old concept, right? It says, is the object's speed increasing or decreasing at t equals 3? So, and you're supposed to give a reason, give a justification for your answer. So if you would, using your calculator, see if you guys can arrive at a conclusion and practice writing out your reasoning for this. And then we'll do number 9. I'll kind of do that one with you. Are going to be deciding this question right here. Is the object's speed increasing or decreasing? What are the things we got to take into account? What do we have to look at? Velocity and acceleration. That's right. So what's easy about this, I suppose, is you already have a velocity function. So to find v of 3, all you do really is you grab your calculator and you plug in a 3. So you get v of 3 equals cosine of 3 times natural log of 3. And what does that come out to be? Negative 1.088. You guys agree with that? Oops, I forgot my negative. There we go. You guys have that same number? Okay, fantastic. So it'd be really tempting sometimes for folks to look at that and say, hey, look, v of 3 is negative, therefore speed is decreasing. But we got to remember what v of 3 actually is. Like, what does v of 3 stand for? Velocity at 3, yeah. So like the fact that velocity is negative doesn't mean that speed is decreasing. At least not yet. It could in combination with the other thing you mentioned. So let's find this, a of 3. So how do I find a of 3 if all I really have is a velocity function? Derivative, yeah. So that would equal v prime of 3. And I'm hoping that you all used Math 8. You didn't have to, but you could have. Either way, whether you used Math 8 or whether you used a product rule, you should get the same number, right? What number did you get? Was somebody offer one up?
Negative 4.85.
Negative 4.85?
Negative 0.485.
0.485, okay. You all agree with that number? Okay. So then this is where we get to make a judgment, right? We look at the velocities sign and the acceleration sign, and obviously they are the same sign. So what conclusion do you draw? Speed is increasing, yeah. So say something along the lines of, because v of 3 is negative and a of 3 is negative, obviously they both have the same sign, speed is increasing. So you guys remember this from first semester? I hope that you do. So basically what you'll find as we go throughout the second semester, most all of the applications that we do will be the exact same applications that we did in the first semester. It's just going to have maybe some other complications like an ln or an e to the something or whatever. Hanging in there? Fantastic. Okay, so then let's take a look at number 9. Number 9, I wrote a little note there. If you guys would read that real quick, I'll read it out loud. It says, because natural log of u does not exist for non-positive numbers. So I'm sure you already knew this. Let's make sure we clear it up. You can't do the natural log of 0. There is no such number where you say e to what power gives me 0. There is no number. Same way, there's no such number as e to something gives me a negative. Just the nature of exponents, right? It doesn't work that way. So because of that, and because we might need to work with negative numbers, and we will definitely be doing this later on during our semester, we need to have a way of dealing with that. And so this is a way, natural log of absolute value of u, right? So if we had this, natural log of absolute value of u, what's the only number that doesn't work now? 0. Yep, 0 still doesn't work, but now all the negatives would work because you know the absolute value just turns them into positives, and still all the positives would work as well. So the point of this is simply this next statement, that the absolute value symbols actually are not going to complicate the process at all. I'll prove that to you. Okay, so check this out. F of x is equal to ln of absolute value of cosine of x. So let's go ahead and do this as if the absolute values weren't there, and then I'll prove to you that this actually works. Fair enough? Okay, so what is the derivative of natural log of something? 1 over that something. Yep, so this would equal 1 over cosine of x times the derivative of the inside is negative sine of x. So this would give us negative sine of x over cosine of x. And if we wanted to be super cool, we would use a little trig identity and actually say that that is negative tangent. Yeah. Okay. So somebody who's paying attention, obviously, is going to look at this and say, wait a minute, you completely ignored the absolute values. You can't do that. And that's really true. I'm using kind of a trick, and I want to prove that trick to you. Is that good? So check this out. If I wanted to prove this to somebody, and I can see why somebody might want to know, I could explain this a little bit better. So I would say that f of x equals natural log of cosine of x if cosine of x is positive. Right? So if cosine of x is a positive number, the absolute values are going to make no difference at all. Or f of x could equal natural log of negative cosine of x if what is true? In what instances does the absolute value demand that we change the sign? If what?
Cosine is less than 2?
Yeah, if cosine was negative. This goes to our basic definition of absolute value. Okay, so do you guys know that you can take just about any absolute value function and you can split it up into a piecewise? We've done this before, right? Yes, a little bit? Okay, yeah. So I just split it up into a piecewise. Now what I'm going to do is I'm going to differentiate. So f prime of x then would equal, I'll do this top piece up here first. So the derivative of natural log of cosine of x would be 1 over cosine of x times negative sine of x, which equals negative tangent of x, if cosine of x is positive. So that's that top piece. And then the bottom piece, well, keep in mind the same principle applies. The derivative of natural log of whatever is just 1 over whatever times the derivative of whatever the inside was. So this would equal 1 over negative cosine of x times what? Wouldn't it be negative sine? It would be positive sine. So then when you look at this, you say, well, gosh, that's just sine over cosine, and it's still negative, and that equals negative tangent. And that's if cosine of x is negative. So I just used the example here of ln of cosine, ln of the absolute value of cosine. This principle still holds true if the inside function was something different. Maybe even just like an x or something. Okay? So the big takeaway, guys, is this. If you're differentiating ln of the absolute value of something, you just proceed as if the absolute values are not even there. They're there, and this is all the reasoning behind it, but it's okay if you just kind of use the little trick of they really don't matter on this. You good? Please, for goodness sake, just use the little trick. Don't re-explain yourself and reinvent the trick every time. Okay, so again, let me pause and just give you a chance to express any questions or concerns you've got before we move on to anything else. Okay, fair enough then. So then the other piece of our day here, as far as newish material, is 5.2, and I think that you probably already know this if you watched the video, that 5.2 is really just the reverse of what we just did, right? The only thing that's going to happen here, the only thing that's really going to come up is Timmy and his issues with the chain rule. That's always whenever you're doing antiderivatives and trying to reverse a derivative, that's always going to come into play. So I'm hoping that maybe numbers 4 and 5, based on you having done the video, might be something you could do. So please try numbers 4 and 5. And just know, Timmy is lurking somewhere and probably messed it up. Oh, watch out. Okay, so number 4. The pattern we're looking for, and I was just talking with Kayvon about this. Basically, up to this point, I probably said something about this in the video, but up to this point in our school year, doing antiderivatives, if the integrand has ever been a fraction, we've basically run screaming the other way. And like, oh, don't make me deal with a fraction. Essentially what we've done is we've always flipped the numerator up and said, all right, whatever that was, we want to make it not a fraction. And this is kind of the first attempt where we've like dealt with a fraction head on and said, there's really nothing we can do about this fraction being a fraction. It's just, we're just going to have to deal with it. This is the first one. We'll look at like 2 other forms like this. There's really not that many that we'll be doing. So with this, no matter of flipping up or trying to cancel things out is going to help us. It's just going to be a fraction. So here's the question we ask ourselves. I mentioned this in the video. I think it bears repeating. We say to ourselves, is the derivative of the denominator equal to the numerator? Numerator. There we go. Something like that. Is the derivative of the denominator equal to the numerator? And if the answer is yes, that means it's perfectly set up. The answer is just going to be ln of the denominator plus c. So when you look at this one, you say, all right, is the derivative of the denominator equal to the numerator? Well, the derivative of the denominator is what? 2x plus 2. And then you look at the numerator, and your answer to this question has to be no. It's not. But isn't it really close? Timmy messed this up, but not by that much. What did he mess up by? Yeah, a factor of 2. So this is a pretty easy fix. All we have to do is multiply the top by 2, and then like we've done before, we multiply the outside by 1/2. This has now fixed the issue, and now it's a perfect chain rule pattern leading to ln. So the 1/2 that we adjusted by goes nowhere, and the antiderivative is simply natural log of the denominator. And I always put this in absolute value, kind of like we finished off that previous section with, and I would encourage you to do the same. At this stage of the game, it's not going to make that big of a difference. Later on, when we get into some more complicated differential equations, it will make a difference. So I think from a habits perspective, we'd want to do that. And that's it. You're done. If you had any questions about this, you could just differentiate your answer and see if, in fact, it does equal the original integrand, and I think you would find out that it does. Okay, so there's that one. You have any questions there? Okay, then number 5, very similar. You look at it, and I'll do this real quick. I won't do this all the time. I'm just picturing you guys doing some quiz sometime and thinking of all the different scary things that somebody might do with something like this. Can you imagine somebody doing this? I don't really like this fraction, so I'm doing this with it. You see somebody doing that? So let's talk about some of the things that would come out of this. Let's say you looked at this and you just said right away, you know what? I think Timmy messed up. Can you see how somebody would say this? He messed up a little bit. I just fixed it, right? Seem reasonable? I think that seems pretty reasonable. And then we say the 3 just goes back inside, and it would be 3x plus 2 to the, oh gosh, what's negative 1 plus 1? Ooh. Do you see how we have an issue? Right. So here'd be a hint for you. I might have said this in the video. If you ever do an antiderivative and you find yourself dividing by 0, do you know what it should have been? Probably should have been natural log. Make sense? Just a hint there. There are some other really scary, like really bad algebra things that could be done here. For instance, somebody might say, oh, let's just do this. Right? Really, really, really bad. Nobody in here would ever do such a thing. Never. Okay, cool. I'll just erase it then. Okay, so maybe you went through all that. Maybe you're like, oh no, division by 0, what do I do? The idea would be eventually that it's a fraction and there's nothing you can do about it. And so we would want to look at this and say, well, since it's just going to be a fraction, is the derivative of the bottom the top? Is the derivative of the bottom the top? No. He's only off by how much, though? 3. Times 3. So I'm going to go times 3 and times 1/3. But this time I've recognized that it's just going to be a fraction, and so it's going to be a natural log here. So it'd be 1/3 natural log of absolute value of 3x plus 2 plus c. Questions? Let me throw one more thing into the mix here real quick. It's really tempting at this point in the game because you're just starting off with this. It's really tempting to think that if the integrand is a fraction, it's just going to end up being natural log, and that's not true at all. So let me give you an example of this. If you had something like this, is the derivative of the bottom the top?
No.
The derivative of the bottom is 3, right? The numerator, however, is x. So if Timmy messes up so bad that he's off by a variable or a function or something like that, that means that he's messed up so badly that we have the wrong strategy entirely. We can't fix it using the typical times this, times that. So please don't be deceived into thinking that all fractions just end up being ln's if you integrate. So, question?
Is it only ln, like the degree of the denominator?
Well, so if you're talking about polynomials, if the degree of the denominator is 1 bigger, then it might be natural log. But I think a better way is to just ask yourself that question. Is the derivative of the bottom the top? If you can answer that question yes or no correctly, then you'll know what to do. Yeah. Good question. Anybody else? All righty. Well, we've got a few more to explore here. Want to help you with this next one. I hope this next one looks pretty familiar to you. Number 6. Come on. There we go. So it gives you a hint of using a trig identity. What trig identity could we use with tangent to get this into a different form? That's right. So I'm going to rewrite this as the antiderivative of sine of x over cosine of x. And I'm hoping that at some point this will look really familiar because we just like 10 minutes ago did something similar to this. So is the derivative of the bottom the top?
No.
It's really close, but it's not quite. What's he off by?
-1.
-1. So what I need to do is multiply by -1 up there. Now we perfectly have that chain rule pattern. And then I have to adjust by multiplying the outside by a negative. And now the chain rule pattern for natural log is right there. The derivative of the bottom is the top. And so the antiderivative will be natural log of the bottom. So natural log of the absolute value of cosine of x plus c. Does that make sense?
Would you put a negative in front of it?
Negative in front of what?
Oh, yeah.
Yeah, there's a negative on the front of the whole antiderivative. Okay. Questions at all? Got 2 more here. We're going to wrap it up. Okay. So number 7 is really interesting. Number 7, it's obviously a fraction. Flipping that denominator up is not going to do anything useful, at least. So let me ask you the question. Is the derivative of the bottom the top? It's not even close, right? The derivative of the bottom is 1. The top is that huge polynomial. So clearly right now is not a natural log, right? So this would be an example where antiderivative of a fraction doesn't seem like it's leading to natural log. Did you notice the degree thing? And Meg, you brought this up. You're like, hey, the degree maybe would have a pattern kind of like this or that, right? What do you see here with the degrees? Yeah, it's big. Yeah, the numerator's degree is bigger. Huh. So I got a strategy here for you. We need to get this into a much more usable form. And I feel like some of you know where I'm going with this, but you're like, no, don't say it. Don't say it. You actually do? Anybody know? Say again? If we could, we maybe would do that. And we'll find out here in a second if that would actually be helpful. But there's going to be one way that'll for sure work. And that's actually to do the division. Because isn't a fraction just a division? But there's a much easier way than that whole long division algorithm thing. Synthetic division, right? You can actually do synthetic division because its divisor is just x minus 2. So this might be a little reminder about what synthetic division is all about. So your divisor is x minus 2. And so if you remember, you have like this little box over here. if the divisor is x minus 2, what number goes in the little box? 2. It's always the opposite of whatever number's in the divisor. So this would be a positive 2. And then taking care to not lose any place values in the degrees, we stretch out to the right with all the coefficients, correct? So it would be 1, -4, 7, and -10. You guys remember the pattern here? If not, I'll refresh. And I'm making a video here, so if you needed to go back and look later, you could watch my video or one of 2,000 other videos on YouTube about synthetic division, probably. Anyways, here we go. Guys, remember what happens with that 1? Yep, comes down directly, so the 1 gets dropped down into our answer line, and then we start the process. What do I do? 2 times 1, and I get 2. I write the answer here. So I did 2 times 1. I did divisor times that 1. Of course, I got a 2. I write it below the next place value down. And then what do I do vertically? I add. That's right, add. So -4 plus 2, -2. And that, my friends, is one cycle of the pattern. And we basically just repeat that cycle a couple of times until we're done. So now I'm going to go divisor times -2. And what do I get? -4. Just like before, I write the answer under the next place value. And then just like before, I add. So 7 plus -4 is 3. And that's the second cycle. Do one more. What do I get for the next product? 6. And again, I add vertically. I finally arrive at the end. And I know I'm done because there's no more numbers to multiply and add. Synthetic division, right? That's our friend. We can do this way faster. So what we're going to do, we're going to reconstitute the polynomial. So if you guys remember, the original dividend was x cubed, and we divided by x. So what's going to be the degree of my quotient? X squared. Yep. So it's going to be 1x squared minus 2x plus 3. And then that remainder thing, we customarily write the remainder over the divisor. So I'm going to write plus -4 over x minus 2. I just kind of rebuilt my polynomial from my synthetic division. Okay, so at this point you might be asking, why on earth is this in the whole section with natural log? You're about to find out. So I'm going to rewrite my integral here. It's going to be integral of x squared minus 2x plus 3 minus 4 over x minus 2 dx. And now I can just go term by term by term because now it's just a sum of these. So what's the antiderivative of x squared? Yep. And how about the antiderivative of minus 2x? That's right.
X cubed for the first one.
Oh, x cubed. Thank you. Antiderivative of 3? 3x. Oh, and then what's the antiderivative of minus 4 over x minus 2?
1 over -4 times x minus 2.
No, there's no 1 over anything. Let me put it like this. I'll pull out the constant. So I get that 4 out of the numerator. So now it's just the antiderivative of 1 over x minus 2. What's the derivative of the denominator? The derivative of the denominator is 1, and so it will be ln of x minus 2. So your final would be 1/3 x cubed minus x squared plus 3x minus 4 natural log of x minus 2 plus c. So that's why it's in here, right? These will often lead to natural logs. Okay, y'all hanging in there? Okay, so the very last one has to do with area. If you guys look at number 8, it says find the area of the region bounded by the graph of y equals x over x squared plus 1, and between the, I think the vertical lines, what is it? The x-axis and the line x equals 3. Okay, so if you want to use your calculator to graph this real quick, you're welcome to do that. I want you guys to try number 8. This will be our wrap for the day. lovely orange region. How do you find the area under a curve?
Can I just set that as a length or something?
Say again?
A rectangle?
So you could use rectangles to approximate the area under the curve.
Antiderivative from 0 to 3.
Yeah, it's an integral, isn't it? And is it, yeah, 0 to 3, because that vertical line is at 3. So let's set this up real quick. So the region starts at x equals 0, it ends at x equals 3. And so Max's idea of doing the integral from 0 to 3 of, and it really is like Eddie mentioned, like a rectangle. It really is kind of a rectangular concept in there. This is the height of the rectangle that you'd be working on, and then dx is the width. So I'm hoping that you look at this now, whereas 2 days ago you would have looked at that and thought, man, I have no idea how to evaluate that integral without a calculator. Now that you've done what you've done here, maybe you can. So let me give you a minute. If you haven't already looked at how to evaluate that, please do. We'll get an answer here, we'll be done. Okay, so did Timmy mess this up? What factor is he off by? It's off by a factor of 2. So to do this, again, we can do this completely without a calculator. I've got to multiply the top by 2 and the outside by 1/2. So if I do that, my antiderivative is 1/2 natural log of x squared plus 1, evaluated from 0 to 3. And then it's just a matter of doing FTC1. So it would be 1/2 natural log of 3 squared is 9, 9 plus 1 is 10, minus 1/2 natural log 0 squared is 0 plus 1 is 1, and Ln of 1 is 0. So if you wanted to, you could write this as your final answer, 1/2 natural log of 10. Although if you left it like this, it would be just as good. If you wanted to be super cool, you could write this. Remember those old rules? You don't really have to do that, but anyways.
What if you evaluated it? Should you not evaluate it?
You mean approximate it with a calculator?
Yeah.
So it all depends on if the calculator is active. If the calculator was active on a question like this, wouldn't you be incredibly foolish to do all that? Just use Math 9, done.
Yeah.
Now you set the thing up and use Math 9 and it's over with just as quickly as you can type. So I would assume that if we went to ln of 10, root 10, probably means that we didn't have the calculator active, so I wouldn't go any further. Okay, so guys, great job. That's all I've got for you as far as new stuff goes. Reviewing, feel free to jump back into